Hi guys, welcome to Learning Electronics Repair and part 2 of this video with this Powermate mixer stuck in protect mode. I will just first mention we're going to take a deep dive here into the protect circuitry of this mixer, and in the last 10 minutes of the previous video, something like that, I explained, showing the schematics, the basic principles of how this circuit works. So if you didn't watch that, please go and watch the last part of the previous video. I'll put a link into this one. So hopefully you've all done that now. We're going to take a deep dive, as I say. So I think for 2 reasons. Firstly, yeah, I need to fix the fault. But secondly, I think this is a really good example of discrete transistor circuitry, not necessarily a particularly simple one. Okay, maybe not overly complicated either, but that depends on your level of understanding. And I'm sure that at the end of this video, you'll understand more about this type of circuit if you don't have much experience of it. We're going to have a look at the voltages we can see. We're going to have a look to see how this is operating under the fault condition, and hopefully we'll be able to see as well how it operates in normal conditions. So let's see if we can fix it, but if not, I'm sure we're going to learn a lot. Come on, let's go. Okay, so let's continue with this repair from the previous video. We have a plan, so let's implement it, yeah? And why not start with the basics? So once again, I'm going to measure all the power rails because we know these are monitored, yeah? And we now know we can power this thing directly from the mains without the current limiter. So minus 15, present and correct. Plus 5, yeah, good. Plus 24, close enough. Plus 15, yeah, good enough for me. Good enough for Gran Canaria, yeah. And then the high voltage supply, so VCC. Minus 80, what we expect. Plus 80, what we expect. So all the voltages are there. That's the first check. Let's just look at these fans, because we know they're both powered from the same place, but only one is working. Can I get a connection into this? I'm not sure. Not so easily. So I've just disconnected them. They're kind of like opposite ways round. So this is reading 0. Minus 26. I noticed the circuit, it was kind of all negative, okay. And this one reads also minus 26. So we have power to both fans, assuming this wire is okay. So it looks like we have one faulty fan, but that won't cause the fault. There's nothing monitoring the fans, yeah. So let's have a look at this time in signal. I don't know if you've realised yet, by the way, that all this kind of runs on negative supply voltages. You see here, so time in should be minus 11. I believe that's when it's operating. It goes up when it goes into protect. From what I recall, I have worked on these things before, or similar. I've not worked on this particular PCB before with this fault. Okay, look, same with the fans. So the fan output is a little bit strange. One end of the fan connects to 0 volts, okay, and the other end of the fan connects to a negative supply, which can be minus 26 for fast, minus 14 for slow, or 0 for off. Okay, so the whole circuit, this you can see again with the output from this op amp, the voltages. So the more negative, the faster the fan spins, and it's all run from the negative supply rail. I don't know why they did that, but apart from sometimes maybe screwing with certain people's heads, it works. Yeah. The other question Detlef asked me, why didn't he just use a microcontroller? Admittedly, the supply voltages are higher in here, and my answer is, well, because it works. Yeah, this works, so why? Why? Anyway, you can talk about that down there. So the next thing we're going to check is this time in signal, and we can see that it comes in on D829 cathode, or D828 anode, or the base of Q15. And all of this circuitry seems to be in this area of the PCB. Here is Q815, so we could go to the base of that, or the diodes we were just looking at. Well, they're here, so 828, 829, okay? And we can measure on the anode of 828. So that's our measurement point. What do we get? Well, time in 12.46. I don't think that's far out of the way. I mean, it's lower than I expected, or rather than it says here. But as I understand this circuit, it looks like all these various things like this transistor and this op amp, yeah, can increase the voltage on time in. That's why we see a diode here, by the way. Okay, and we see another diode here. So these diodes effectively separate these signal sources from each other, and if any of them is higher than the voltage that was there, the voltage there will go up. Yeah, it'll push the voltage up. And I think that's how this thing triggers. We'll just go on that basis for now. So let's have a look at this. So I think that is probably about right. What do we see on fan trigger here? I'm assuming we're going to see voltage here because we know that the LED is on. Okay. For the LED to turn on, well, this end of the transistor, the emitter, is at VSS minus. And we see that as here, VSS minus. So that's minus 28. Minus VSS is minus 28. Okay. So this is at minus 28. To turn the LED on, I'm assuming you turn this transistor on. So the actual base would have to be above minus 28. It's through a 100k resistor, so the voltage here would be somewhere above that at least. Let's have a look. So we can measure on Q811 collector. We can see the emitter is at minus 28. Okay, so we can measure there, or we can measure either side of this resistor, 876. Well, I can't easily see where that resistor is, so we'll go for the transistor because that's easy to find. So, collector of Q811. 0.12. Positive. What's on the emitter? Minus 27. Yeah, that's the negative rail. Base. Minus 27.3. Let's just go back to the emitter. Minus 27.4, so that should be switched off, and we have 0.012 here, so it looks like it is switched off. Looking at this now a little bit more, yeah, so we have 0 volts here. Now you can see here we have 3 resistors in parallel, okay, each one is 220 ohms, and that should have minus 24 here. Now this is a diode which is going to ground, but that's reverse biased if this end is negative. We can see here relay drive, and there's a relay. Now this relay is not switching the speaker, which is what I assumed the relay would be doing, but you know, assumptions often lead you the wrong way. So that relay is actually shorting out the thermistor. This is where the mains comes in, okay, to the transformer, and we have a NTC here. Okay, this is normal to have a relay across it, so this is effectively limiting the inrush current. Okay, and when the amplifier powers up, we short that out with the relay. Now I don't hear the relay go click. That's the first thing I'll note. I don't hear any relays go click when we power this up. So that suggests that this is wrong. To power that relay, I mean, it doesn't tell you the voltage of the relay, but I think 24 is a good guess because that's one of the supply rails we do have. So one end of the relay, ground, okay, and the other end, relay drive, minus 24. So that tells me this voltage is correct in normal operation, which is what you'd expect it to be. So there should be minus 24 here. Now the minus 24 can't come from there, that's ground. there's something else here, relay drive, which suggests there's another connection going down this way. In fact, if we follow this line downwards, well, that just takes us to the mixer page and stuff. I don't think that drives any relays down there, but where I think it might drive them is on the amplifiers, which are up here. Okay, so yeah, we see it there. There's a relay on the output of the amplifier, and that also gets switched on by relay drive. And for sure there'll be one on the other channel as well. Yeah, there. So in fact, that signal actually switches 3 relays. What we can do is measure either side of these resistors, okay? But I can say pretty much straight away, if there was minus 24 here and 0 or thereabouts there would be 24 volts across the resistors. And each one is 220 ohms. So that's like 100 milliamps each. There'd be 300 milliamps flowing. You'd expect those to warm up somewhat. Okay, so let's have a look. So R818, 819, 820, which are actually here. And we can just check this. Yeah, that connects to there, to there. So they are in parallel, in fact. Okay, and then the resistors would measure roughly 70 in parallel. Yeah, 73 ohms. So they're also okay. So let's have a look there. I'm not totally sure at the moment which end is which, but I'm interested to see what I see. Okay, volts. Point 1. Point 1. Well, they're going to be the same in parallel. What's here? 0.12. Okay. Both fans are running now, by the way. Don't really know why, but they're both running. Magic fingers or just scared them into working. Okay. So we can say with good confidence now, the voltage here is wrong. Okay. Obviously, the voltage there is wrong. That's why the protect LED is on. The fans are running at full speed. All because the voltage here is wrong. And I think likely, although I can't say 100%, the voltage here is correct. So I think what we'll do next is we'll just check all these transistors here. Certainly those 3 and those 3. And let's see if we spot any problems. You could do this one of 2 ways, or maybe even more than 2 ways. Yeah, one would be to work your way back through the circuit, measuring voltages. You should be able to figure out if a transistor is supposed to be switched on or off, because we know what should be coming out. Okay, and we know what's going in. Other option would be just to go through all the transistors in that circuit and just test them in diode mode. So I'm going to do that first. We may end up doing the other way afterwards. So I have the multimeter in diode mode there. I've made a note of all the transistors that are in that part of the circuit, and I've made a note of whether they are NPN or PNP. So we'll start with Q809. This is a PNP. Diode junction. Diode junction. Negative to the collector. This would be the normal polarity of operation. Means open. Okay, 810 again, PNP, and they marked base collector emitter, or at least the collector and emitter are marked. Junction, junction, let's see, this is the emitter, this is the collector, I think. Okay, you can't say always what you'll see there. We could look at the schematic, but it's not short or open circuit base emitter, base collector. 811. This is an NPN transistor. Reads like a junction. Reads like a junction. Just climbing up like a capacitor charging. Okay. Continue. Next one is 812. I don't just see that at the moment. We'll come back to that one. 813 is a PNP. Let me see. Looks okay. Okay, just capacitor charging there. Okay, 814. This is another PMP. In fact, there's mostly PMP in this circuit due to the negative supply rail. Looks like a junction. Looks like a junction. Capacitor in the circuit somewhere there. 815. I think that's actually this one. Yeah, it looks like 815. Can we get under that way? Yeah, I think so. PMP again. Looks okay. 816, 812 we still need to find. Well, there's 816, another PMP. Oh. Well, that means almost like a short base emitter. This could be connected as a current source type thing, a current mirror where you have the base emitter connected to each other. But let's just check that one on the schematic. That's actually this one. I don't see why that should read such a low resistance. I mean, we have 1.3k or 13k. No, 13k. That's suspicious. Okay. Let's just find the ones we couldn't find. So we still have 812 somewhere. And there's 821 and 825. Well, there's 821. This is an NPN. That looks okay. So now we have 825 and 812. If we can't find them, we'll come back to the one that looks suspicious. What's this thing? 812. Well, that's where that one was. Okay. This is a PMP. Looks okay. Looks okay. Yeah, positive to emitter is open. That would be the normal polarity of operation for a PMP. So that's okay. Just 825. And that is right next to it here. Okay, so this is an NPN. Yeah. Yeah, positive collector. Reads open. Okay, so we have one suspicious looking transistor, which is 816, which is a PMP transistor. And we can see a unusually low voltage between the base emitter. Okay. What about collector emitter? Reads open. Base collector reads okay. So we seem to have a base emitter problem. What's that in resistance range? $60 ohms. Okay. Well, it's not like a standard value. I mean, you know, 47, 56, 68. We're going to have to take that one out. Now, we could take this PCB out, but we have to get all this off. We have to get this metal shielding off. Then there's a lot of bolts holding this down. It's a bit involved in actually disconnecting this. So there is one other thing I would like to just try first. If we look back at our schematic, so this is the transistor under suspicion. Now, we have the base connecting via a 13k resistor to ground, okay? We have the emitter connecting to the plus 15 volt supply. So if there was a problem here, what happens is, if the transistor turns on via this diode, it increases the voltage here. Yeah, plus 15, that would increase the voltage here. Much the same as this op amp would do, I think, by the way it's wired up. Yeah. if the non-inverting input goes above the inverting input, and the inverting is just the reference. If this goes above that, output would go high. There's a feedback resistor in there, positive feedback, okay, and then this time in would go up, which again would raise the voltage here. And I mentioned earlier, I thought that's the way this worked. So it's possible this is okay, and we're actually seeing the resistance of this PTC, which we know is here inside the transformer, and that connects to this little connector, CN14 by the looks of it. And that is this one. That's this one. We can see, I'll just unplug it first, but I'll show you. So that goes up here together with all these and disappears into our transformer. So let's unplug that and measure that transistor again in diode mode. So PNP transistor, emitter, base now reads okay. So that isn't faulty, at least it doesn't appear to be faulty from the meter at least. All the transistors look good then. I mean, there are some diodes in the circuit around here. There are resistors. I mean, there could be some other fault in this circuit. I think we're going to have to trace this through by checking through the voltages. And we should start with this point because we know this is wrong. Okay, I've printed this out, this part of the circuit, so we can mark the voltages on here. Yeah, my printer needs fixing, but you know you never get to fix your own stuff, do you? So we'll put the voltages on and then we'll work out whether this circuit is actually behaving as it should do for the given input voltage, okay? So we'll start with this one, Q811. And from what we can see is happening, this is switched off. We know because we don't have the minus 24 volt supply here, okay? Q811, emitter, minus 27.3, collector, 0.12, base, minus 27.27. So that is definitely switched off, okay? The base is almost the same voltage as the emitter. So for that to switch on, there needs to be a voltage drop across this resistor, which means current needs to flow through the resistor. And the only way the current can flow is through here and through this transistor. So this transistor needs to be switched on, okay, for that to be switched on. Let's have a look. Q812. And while we're here, let's look at Q813 as well. Q812. Collector, minus 27.2. Emitter. Oh, it's switched off. And the protect light's gone out. While I was measuring that, it switched off and the protect light went out by itself. Well, I say switched off, the fans went off, which is what you would expect. That's interesting. Let's have a look to see what is happening on this signal timeout. So this is the anode of D828, okay, anode 828. Yeah, what happens here? So fans are on, minus 12.39, 12.4. And it goes to minus 12.6 when the protector goes off. You hear the relay click. Strange. Well, I wasn't sure what to expect, but it wasn't that. Okay, power it up. Protect, power on. Wait. Protect goes off. Takes a little while though. Well, this is unusual really, and here I am. I can see myself on here, okay? So this is the previous Powermate 1000 I looked at. This is the same model, so with the 1600 amplifier board in it. And the customer had this one back. It needs a transistor, one channel's badly distorted, parts are on order, but he's using this at the moment with just the one working channel. And I'm just going to show you on this one what happens when we power it up. Violent. What happens? So you can see the protect light came on for a second or so and then goes out. Okay, but ours takes some time to go out. So it's definitely behaving differently from that previous one. Well, that was a bit unexpected, guys, to be honest. But you can see it's not the case I just wasn't giving this enough time to come out of protect. Well, I wasn't. Yeah, fair enough. But the way this is behaving isn't exactly normal for one of these mixers. We have a better understanding then of what's happening here. The voltage here, although it says should be -11, even at -12, this circuit isn't effectively coming out of protect. At about -12.5, it is out of protect. So either we have a situation whereby this is just wrong, this marking. I don't have the other one here to compare with. I wish I did. It will come back again when the spare parts are here. Okay, so if we can't figure this out, we will have that back. Could be this one is just a different revision of this board, so possibly difference in the values of components here would cause the threshold to change effectively there. Okay, I did just point this out as an add-on, if you like, in the first video, why we have two of these circuits, because they seem to be basically doing the same thing, so why do it twice? And the best I can come up with is this capacitor. So when this first circuit triggers, okay, for the voltage here to rise, it has to charge this capacitor. So via the transistor, 68 ohm, yes, it's a voltage divider with this 220k, but most of the voltage is across here, the higher value resistor. Okay, so this will take a finite amount of time to charge up before it triggers the next one of these comparators. And then when that switches off, well, this has to discharge via this resistor. Okay, I don't see it can discharge that way because of that diode, so it would take longer then for the protect to come off. And I'm pretty sure that's to stop either the protect circuit continually activating and deactivating, like chattering, if you want to call it, like the relays chattering away. And also maybe just like a momentary condition that would cause a protect. This stops that from actually causing the protect, you know, some sort of instantaneous thing like a spike or something. So I think that's what that's doing. And that's why we have two of these circuits. But what we can do is we can figure out which of the 7, 8 circuits are actually the ones that are holding this into protect for some seconds, and then it comes out of protect. And the way we can do that, if you look, you'll see that this circuit, for example, the output of the circuit comes via a diode into time in. Okay, so we know time in voltage goes up or less negative when it's in protect, and this diode can only conduct positive to negative or less negative to more negative. Okay, so obviously that diode has to conduct to increase the negative voltage here, and the same with the op amp. Look here, same thing. Okay, and we'll find the same on all the other circuits that drive time in. Well, this one comes through two diodes anyway, operates in a slightly different way. Okay, this one that monitors the HT rails, plus and minus, look, through a diode, time in. And the last one, which we know monitors the speaker out, through a diode, and a resistor in this case, but still through a diode to time in. So any of these circuits can make time in less negative, more positive. Okay, basically then we have an arrangement like this. So we have time in, and we know that at -12.5 this amplifier comes out of protect. Less minus than that, it's in protect. Okay, and then we have the various things that we're sensing. So heatsink temperature, transformer temperature, the right channel amplifier, plus and minus HT, so that's the plus and minus 82, speaker out, okay, same for the left channel, plus minus HT and speaker out, and then the 28 volt AC supply, which has two diodes like that, and all of those can affect the voltage here. But if you think about it logically, if any of these is more negative than that, they can't affect that. They can't make it more negative, okay? And that is because the diodes are reverse biased, apart from this circuit. Yeah. I'm wondering actually, because this is AC, whether this is something to do with that capacitor, which seems to act like some sort of time delay in the trigger circuit. There may be some other capacitors in here though. Okay, so we can see anyway that any of these being more negative than that can't affect that. But any of these being more positive or less negative than that will control it. And whichever one of these is the least negative, that's the voltage we will see there. Take into account, of course, there's about 0.5 volts drop across any of the diodes, okay? So to see which one of these is controlling that at any time, all we need to do is measure the voltage drop across the diode. Yeah. If they're forward biased, then they're the ones that are holding that down. So that's what we need to do next. Let's find out which signal of these holds that and protect for several seconds when we switch on. I've marked the actual component numbers for the various diodes so we know which ones they are. And just to absolutely clarify this, whatever voltage on here, say minus 12.5, okay, that will be set by whichever one of these is about half a volt more positive than that, or if you like, less negative than that, okay? Let's find all these diodes and let's have a look to see what's on them. Let's look then to see what is on the diode. We know this end, if it's still doing the same thing, we'll go from about minus 12 to minus 12.5. The fans will switch off, the tap will go off. Does this end change? So minus 12.15. And would you believe it, the fault is back, okay? So it's intermittent. Well, time in, 12.46, drifting up slightly. Okay, 12.47. And this end, 12.2. So this end is actually more positive than that end, okay, but only by 0.27 of a volt, which doesn't seem to be enough, I would think, to actually cause that diode to conduct. In fact, we can see the diode, yeah, about 0.58, okay, so that can't be conducting. You don't suppose if this electrolytic capacitor here, C824, is leaking, it might cause this problem? Well, I would have to remove the PCB really to change that properly. But what I can do, because this thing was kind of intermittent, I can try warming that up with hot air a little bit and see if this thing then works again. Well, there's one good way to find out. So switch on, just give it a few seconds. Fans are running. We are in protect, okay. I'm not saying this is heat sensitive, this fault, but it might be. No, apparently not, okay. Or at least not in that part of the circuit. So I'm still not sure what the intermittency was. To find the rest of these diodes, Well, in one respect it's easy-ish because I think they're all this type, the red ones, 1M4, 148, so they kind of stand out a little bit, make them a little bit easy to find. But then it's probably going to be difficult because some of them, I'm pretty certain, are going to be at the back of the board over here behind the amplifiers. These will be the ones that actually monitor the HT voltage rails and the speaker output. Okay, so I'm going to have to take all this off, I think. There's another good reason probably why as well, because we know we have this intermittent issue and we still haven't figured out where the gin and tonic went yet, and it could have gone in the back of there, and that could also be in some way related. So let's get this off and let's figure out where all these diodes actually are. Okay, I've got the PCB out. So this is like the piece of card or something. It's a bit stiffer than card that fits underneath it. There's a little bit of discoloration here, like maybe this is where some liquid did go in. It's not heavily discolored. And the PCB is kind of raised up on these little plastic things, but it's possible that was touching the PCB just there. The board itself looks clean, really, if you look underneath it. Again, looks clean, don't see any obvious issues. But if we zoom in, especially up towards this back end of the board, we do seem to have some sort of contamination in this area. In fact, generally at the back of the board, really. Okay. I mean, this is fairly typical for these things anyway, but yeah, it looks like something might have got in there. So that's possibly where the G&T went. I assume the story is correct. We can now see some of the diodes. So I've drawn like just a rough layout here because I need to know where all these are and then put it back together so I can actually measure them, yeah. And knowing me, I'll forget where some of them were. So we can see here D318. That's this one, and 319 we need to find. So I'm just going to draw these on my diagram. D318, D319 is down here next to that capacitor. Yeah, that would suggest that the other side there's D518, okay, and D519. Okay, so I just draw a few landmarks like the hole in the PCB, 2 transistors. We know these big resistors are here, so it just basically shows us where the thing is. 3 more to find then. 800 and 801 are down here at the front, okay, and the last one is here, D823. Okay, this is the TL074. We saw that part of the circuit with the 4 op amps. Okay, so we found that as well. I don't need that one, but I've just noted it so we know where that is. So the repairman in me tells me to clean all this up. It's not so bad as something been on that side, but to clean all this up and see if it works. Yeah. But since we are on this epic journey of discovery and education, let's carry on with what we're doing. Let's have a look at all these diodes to see which one is actually driving the time in rail to the voltage it is at. Yeah. Let's look at these diode voltages then. This one's a bit awkward to get to at the back, but I think it's okay. So switch her on. Minus 80 on that one. Okay. So that's here. Okay. D519. Okay. Minus 12.4. Which is there. So 318, 319 at the back on the other side. Okay, 318. Minus 80 again, 80.5. And 319. So a little bit further forwards. Yeah, here. Okay, what's this one give us? Minus 12.3. I'll know if it comes out of protect, by the way. We don't have the fans on, but I'll hear the relays click, yeah. So 823. This is heatsink temperature, 14.36, okay. And then we have the junction of D800 and 801. The cathode end we want to look at on these because they're the opposite way round. Okay, what do we have? What I say about minus 1.6. Remember, this is AC. Let's go to AC on the meter. 17.6. And time in. DC. Minus 12.63. Okay, so this is what we have. That is timing, and it's changing. Yeah, you can see that as things warm up probably. So heatsink temperature, this end of the diode is more negative than that end. So that can't be conducting, okay? Transformer temperature, PTC, this end is less negative than this end, so that could be conducting. I mean, we have about 0.43 volts of a difference there. You think that probably isn't enough to actually really conduct. This one here, minus 80. This end is way more negative than that end, so that can't be conducting. Reverse biased. Right channel speaker, minus 12.4. Well, it's a little bit lower than that again, but probably not enough to make the diode conduct. Okay, minus 80, definitely reverse biased. Minus 12.3. Again, probably not reverse biased enough. Okay. And this has 17 volts positive AC on the end here. So you would assume that that point is far more positive than that point, so that can't conduct. And the other one I didn't measure, but we'll do it now. 17.5. So those are reverse biased as well. So it would appear there is some problem in this protect circuit itself. We now have minus 12.6, but it's still stuck in protect. Previously, when it was being intermittent and coming out protect after 10 seconds, it was minus 12.5. So it would seem to me the problem is somewhere in that circuit. But considering we have all this mess at the back of here, we may as well take this apart, clean it all up first before we put it back together. So we appear to have an intermittent fault, okay, within the actual fault detection circuit itself after the time in signal, because we can see it's behaving differently even with the same sort of voltage on time in. Okay, warming the capacitor in that circuit didn't help. Obviously it may not be heat dependent, this fault, it could be dependent on something else, and basically I need to find it. Yeah, but I expect some of you will say, Rich, try this, try that. Okay, so I'm happy to do that sort of thing as well. If there's some suggestions, try this, try that. You can all see the schematic. I'll link it in this video so you can download that yourselves. Yeah, and let's see where we go. Okay, hope you enjoyed that and look forward to seeing you all very soon on Learning Electronics Repair. Ciao for now, guys.